Good day and welcome back for the third and final installment of our discussion on the fundamental theorem of line integrals. And in the previous two videos we've introduced the underlying concepts, but what remains is just investigating a few additional examples. And note these questions can come in multiple different forms. One of the ways we can ask, and will ask the questions, is to find the work done by a given vector field and moving a particle along a curve which we described for you. And recall, when it comes to calculating the work done by a vector field, we can always think of work as being the line integral over the vector field, where in this case, this vector-valued function r of t is giving us a description of the curve C. And we could immediately jump into our method from the section on line integrals and just computationally try to evaluate this. But note, in order to do so, we would have to substitute our curve into the vector field. So for example, each x would have to become cosine of t, and the y would have to become 2 sine of t. So immediately it looks like it would become rather involved and maybe a difficult problem. Part of our thought process in this case is going to be to ask a simple question. Is the given vector field conservative? If the vector field is conservative, then we will attempt to apply the fundamental theorem of line integrals. And remember, as we discussed at the end of the previous video, this is something that we can quickly check. If we think of P and Q as the components of the vector field given by F, we simply need to check their partials. P sub y is equal to cosine x. Q sub x is also equal to cosine x. And because those partials, P sub y and Q sub x, are equal, that is the first component partial with respect to y, the second component partial with respect to x, we can conclude that the vector field is conservative. And note, this just provides a starting point. Once we know the vector field is conservative, we would like to apply the fundamental theorem of line integrals, which means we need to know the potential function. That is, can we find a function little f where the partial with respect to x is p and the partial with respect to y is q, the so-called potential function? So what we need to do is find f with the partial with respect to x is y cosine x, and the partial with respect to y is sine of x. And note, if we were meeting face-to-face in class, this is a point where I would typically hit pause and kind of turn the floor over to you. And I recommend you to do the same thing here. Pause your video and take 4 or 5 minutes and see if you can finish up this example. So assuming that you've done that, and if not, I strongly encourage you to do so, we will undo these partial derivatives. So that first equation tells us that f is the antiderivative of y cosine x with respect to x, which would be y sine x plus a constant, remember possibly involving y's. From the second representation, we know that f should be the partial antiderivative of sine of x with respect to y. So y sine x plus a constant now involving x's. And we should be able to combine these two representations together to come up with a single representation for f. And note in this case, the only term we have is the y sine of x. So we will simply let c sub y be 0 and c sub x be 0. The fundamental theorem of line integrals now allows us to get started with evaluating the line integral to give us work. It implies that we get back f evaluated at the finish point of the curve minus f evaluated at the start point of the curve. And our curve is described by this vector-valued function as t varies from 0 to 3 pi over 2. That implies we start when t is 0, we finish when t is 3 pi over 2. So symbolically, we can say r at 3 pi over 2 would represent the finish point, and r at 0 would represent the start point. And let's just do a couple side computations. R of 0 is cosine 0 comma 2 sine of 0. Cosine 0 is 1. Sine of 0 is 0. Similarly, r of 3 pi over 2 is cosine of 3 pi over 2, comma 2 sine of 3 pi over 2. And note, cosine of 3 pi over 2 is equal to 0, and sine of 3 pi over 2 is minus 1. So the end point of our curve is the point 0 minus 2, and the start point of our curve is 1 comma 0. And just to note, I don't want you to be alarmed, but we are abusing notation. We are using this vector r of 0 and r of 3 pi over 2 to represent points instead of vectors. It's just that's the convenient and the conventional way to do it. Substituting into our function f that we have to the far right, we would have minus 2 sine of 0, which is 0, minus 0 sine of 1, which is also 0, which tells us that the work done by the given vector field in moving a particle along this path c is equal to 0. And before moving on to the second example, I just want to remind you that the wording of the problem can most definitely be similar to what we see here. We give you no indication that the vector field is conservative, or no indication that you should apply the fundamental theorem of line integrals. So checking to see if a vector field is conservative needs to be part of the thought process we have when we approach these problems. So let's go ahead and look at a second example. Evaluate the given line integral where c is a line segment connecting the point 1, 0 to 2 pi over 4. And similar to our previous example, this is a point where I would again turn the floor over to you. A great opportunity to get some practice. So pause the video and evaluate the integral. And let me give you a hint, which is probably unsurprising. I recommend thinking about applying the fundamental theorem of line integrals. Hopefully you've taken a few minutes to evaluate this line integral, and the observation that I would like to make is it's of this form, a line integral p dx plus q dy, so it's really a line integral over the vector field p comma q. And as we are talking about the fundamental theorem of line integrals in this section, and we very clearly have an identified starting and finishing point, it makes sense to ask, is this vector field conservative? That is, what are the partials p sub y and q sub x? P sub y is secant squared of y. Q sub x is also secant squared of y, which tells us the vector field is conservative. And in order to apply the fundamental theorem of line integrals, we need to find the potential function. And I'm going to leave a few details to you for practice, but in this case, note the vector field is the gradient of little f, with little f being equal to x tangent of y. And note that this is something you can easily verify. The partial with respect to x is tangent of y. The partial with respect to y is x secant squared y. So this very clearly is the gradient of the given function little f. With that observation in mind, we can now apply the fundamental theorem of line integrals. And make sure each and every time you apply the fundamental theorem of line integrals, you tell me that you are doing so. Otherwise, I will subtract some point or fraction of a point, and you probably will not be happy with me. So we have f evaluated at the endpoint of the curve minus f evaluated at the start point. So that would be 2 tangent of pi over 4 minus 1 tangent of 0. Tangent of 0 is 0. Tangent of pi over 4 is 1. And we end up with a final solution of 2. This completes our discussion of the fundamental theorem of line integrals. But as usual, let me make the following observations. You have plenty of good suggested problems to work from the book, and if you have questions, feel free to reach out to me, drop me an email, or stop by virtual office hours. Furthermore, after we finish up our next section, we will have a worksheet that combines together all of these key ideas we've encountered related to line integrals. So we will certainly be revisiting this topic as well. Stay tuned and take care.